We're going to look now at the difference between speed and velocity, as well as the ideas of instantaneous velocity and average velocity. I'm going to do my best to illustrate these ideas with an example of a person running around a track. So we have a track, and let's examine when a person runs. Let's say they started here and they ran to here. And on the clock, that took 15 seconds. And given this particular track, let's say that distance was 125 meters. Now, you can watch the previous video as to what that means by that's the distance. And if that's their distance, their displacement, which is their change in position, is the final position minus the initial position. Now we could say, make this the origin, so our initial position is 0. Our final position would be then the same as the displacement because you'd be subtracting 0. Our displacement is 80 meters at an angle of 45 degrees. And let's make that north. So our track is situated such that this is facing north. Our person started here and they ran to here in 15 seconds. In those 15 seconds, they ran a distance of 125 meters, and they ended up 80 meters in a straight line from where they started. Their change in position was 80 meters, and specifically, it was 80 meters, so I'm going to write that out as displacement. Our change in position was 80 meters north, 45 degrees east. And again, the 125, that's your distance. Okay, so let's look at speed, average velocity, talk about the idea of instantaneous velocity. Speed is distance over time. So if you just have that triangle written down on your page, if you're looking for speed, just cover it up. It's distance over time. And then if you have to do any rearrangement here, distance is speed times time, or you could calculate time as distance divided by speed. So our speed in this case, well, let's just write in the values here. The distance is 125 meters. And the time that took is, or was, 15 seconds. So speed, 125 meters divided by 15 seconds. And that makes our speed 8.33 meters per second. Now there are 3,600 seconds in an hour and 1,000 meters in a kilometer. That makes your conversion factor 3.6. So I could take my 8.3 meters per second, multiply it by 3.6, and that would give me 30 kilometers per hour. That's a coincidence. It worked out even. I did not even plan that with these numbers. So 8.3 meters per second, and if you multiply by 3.6 to convert it to something you're familiar with, that's 30 kilometers per hour. And, well, I guess YouTube's worldwide, so if you're watching this from the United States or perhaps England, where they measure in miles to get a perspective on that. You can take your measure in kilometers and you can divide it by 1.6, and that becomes, it's actually 1.609. That becomes 18.6 miles per hour. So that's also, or 18.6 miles per hour. So 3 different ways of measuring their speed. But in all those instances, speed is simply distance divided by time. So as this person ran around the track, they started here, they ended here, they ran a distance of 125 meters. They took 15 seconds to do so. They were running at a speed of 8.3 meters per second. What was their average velocity? Your average velocity is your displacement, that is your change in position, divided by the change in time, that is the amount of time that took. Although we ran a distance of 125 meters, our position really only changed by 80 meters. Because you're running around a curved track, you don't end up as far away from where you started as you actually ran. The only way you can end up as far away from your starting position as you actually ran is if you run in a straight line. If you ran off the track, you could run 120 meters and end up 120 meters away. However, if you run 125 meters around a curve, you will end up a shorter distance away than where you started. Your average velocity we define as the change in position divided by the amount of time that took. Now, all of these are vectors, meaning we must specify a direction. Our change in position was 80 meters, and remember that was north 45 degrees east. And if you ever forget your east from your west, you'll see me always twitch my hand when I'm trying to figure out if it's west or east. My dad told me this as a kid. It's just west and east spell the word we. So we goes this way and W is on the left, E is on the right if you're facing north. Obviously, if you're facing south, that rotates it around. Okay, so we have 80 meters north, 45 degrees east, and we're dividing by our time, and our time was 15 seconds. Remember, that was the original problem we were looking at, a person running around a track, starting here, running that curve, and ending here 15 seconds later. So our average velocity was 80 divided by 15. Our average velocity is 5.3 repeating meters per second, north 45 degrees east. So what does that mean? It means this. Our athlete runs, they start here and they run at a speed of 8 meters per second, 8.3 meters per second along a curve. And in 15 seconds, they've run a distance of 125 meters. However, if their coach starts beside them and their coach runs in a straight line, and coaches tend to be older and slower than the athletes, coach runs in a straight line this way at a speed of 5.3 meters per second, along that angle, they will arrive at this point at the same time as the athlete. The athlete runs this way, the coach runs that way, but they both have the same average velocity. So over the same time interval, they're both going to have the same change in position, meaning they're both going to have the same displacement. What is the instantaneous velocity? The instantaneous velocity is constantly changing because the direction of the runner is constantly changing. You can think of velocity. So velocity is the change in position divided by the amount of time that took. However, the velocity at a particular time is the change in position in that moment in time divided by almost no time at all. This is a calculus idea, and I've aimed this video at introductory physics students, so I don't want to overwhelm you with the idea. I can do another one going over exactly what that means in detail. In fact, all the analysis of physics is a lot easier with calculus. It was invented by Newton to support it. Your instantaneous velocity is, you can think of it at a particular time as being the speed and stating the direction. That'll work. That's your instantaneous velocity. Now, the instantaneous velocity is only valid at a particular instant. So, in our example, as we run around this track, that instantaneous velocity is constantly changing along with the direction that we're running. So, if I was to look at the instantaneous velocity at time is equal to 0, the velocity we started at, remember we calculated our speed as 125 over 15, so our speed was 8.3 meters per second. The instantaneous velocity when they started out running, they were going due east, so the instantaneous velocity was 8.3 meters per second east. And it looks like if they took 15 seconds to get there, maybe they were at about 11 seconds here. So their velocity at 11 seconds could have been 8.3 meters per second north. Their velocity at about 5 seconds, that's a 5, not an S. So 5 seconds into it, they were heading in this direction along that curve. So their instantaneous velocity at 5 seconds could have been 8.3 meters per second. And let's call that north 45 degrees east. Notice at any given point in time, the instantaneous velocity, so notice this is not a number that's being multiplied by v. I'm using what we call Lagrange notation. So v is our velocity, which is a vector, and it's a function of time. So at these different times, we have these different velocities. And these are all different instantaneous velocities, and what makes them different is the directions in them are different. Okay, so to summarize, you have speed, and speed is simply distance over time. You have average velocity, and the average velocity is the displacement, which is the change in position, divided by the amount of time that took. And then your instantaneous velocity, how fast you're going at a particular moment, is equal to the speed that you're going at that time, while also stating the direction. This also has a direction because displacement has a direction, but I don't need to clarify that because I'm telling you we have a vector here. And when we divide this vector by time, it still has it keeps its direction. And you don't divide the direction out. The instantaneous velocity is the speed, yet also stating the direction.